بسم الله الرحمن الرحيم. الحمد لله رب العالمين، والصلاة والسلام على خاتم الأنبياء والمرسلين نبينا محمد وعلى آله وصحبه أجمعين. This is chapter 7, Techniques of Integration, and we will start by one of the techniques, which is integration by parts. The integration by parts came from the product rule for differentiation. You remember to find the derivative of f times g, the formula is you multiply f times g prime plus g times f prime. So this is the product rule. And we studied in indefinite integrals that if we know a derivative of something, then the integral of the right-hand side should be equal to f of x times g of x. And if we expand this integral, the integral of sum would be sum of integrals. So we have two integrals equals fx times g of x. And if we take this integral to the other side, then we will have integral f of x times g prime of x dx equals f of x g of x minus integral g of x f prime of x. This is the integration by parts formula. We usually prefer to write it in another way. So if you take f of x u, so this would be u. And if you take g of x v, okay, so this would be v, and this would be v, and this would be u. Then u equals f of x, so du would be f prime of x dx. So f prime of x dx would be du, and uv equals g of x, so dv would be g prime of x dx. So g prime of x dx would be dv, and we can write the formula like this: integral u dv equals uv minus integral v du. So we will have an example like this: two functions, product of two functions. We cannot use here substitution because there is no function inside a function, there is no composition. If this were x squared, we could have used here substitution because x squared now inside sign, and we can take x squared as u, and the derivative would be outside. You just multiply by 2 and half outside. But it is not x squared, it's just x. So here we have product of two functions, so we need one of the function to choose it to be u, and the other part of the integral will be dv. So here, let me give you a formula to work with. If we have logarithmic function, we take it u immediately. If not, this is inverse trigonometric, like tan inverse, sine inverse. A is algebraic, x squared. So here x is an algebraic function. T is trigonometric, sine, cosine. So sine is t and x is algebraic. A before t in the word layat. So we take a by u. So the function who comes before, we take it as u. E exponential, like e to the power x, and all the exponential functions. So we will take u as x, and dv would be the remaining part of the integral, which is sine x dx. The function that we take as u, we find its derivative. So du would be dx because the derivative of x is 1 dx. And the function that we call dv, we find its integral. So what is integral dv? It is v because the derivative of v is 1. And integral, so the integral of dv is v, and the integral of sine is negative cosine because the derivative of cosine is negative sine. So now this integral, which I'm going to call I, so I would be equal to, the integral I would be equal to, according to the formula, uv minus integral v du. So in fact, if you use this uh, way of writing, then now you need to multiply this, okay, then this one. So it would be this times this, u times v, or x times negative cosine. So I will write it negative x cosine x. And then minus this times this, okay, v du. I have negative cosine x dx, so integral, of course, negative cosine x dx. So notice that this method, integration by parts, doesn't solve immediately the integral. Rather, it changes the integral to a more simple or simpler integral. So usually, the new integral should be easier to solve, to integrate. If it is not easier, then there is a problem in the choice of u and dv. But if you follow this formula layat, you will not have this problem. So the final answer would be negative x cosine x minus times minus plus, and integral of cosine is sine x plus c, so that's the integral of x times sine x. You can check your answer by finding the derivative of this function. The derivative should be equal to x sine x. Remember to use here the product formula to find the derivative of negative x cosine x. So this is the pattern we use, u du and dvv, and then we go like this. If you choose in this example, if you choose sine x to be u and dv to be x dx and find du and v, you will get this. And the new integral would be more difficult than the original one, because in the original one we have x to the power 1 times sine, and now we have x to the power 2. So this proves to you that we are not going anywhere here if we continue like this. So we need to choose u to be x, not sine x. All right, in this example, integral ln x dx. In this example, I choose ln x to be u and dx dv. Okay, I don't have product of two functions, but here the situation and integration by parts helps us to find the integral of ln x or sine inverse or tan inverse or any inverse trigonometric function. So this is the method. You take u ln x. What is du? The derivative of ln x, 1 over x dx. And then you take dv equals to dx. Integral dv is v and integral dx is x. And now we use the formula. This times this and then this times this. Okay, so the integral, this integral would be equal to, or let me call it I, and I is equal to uv, which is x ln x, this times this, minus integral this times this v du, x times 1 over x dx. And what is x times 1 over x? X cancels with x and you get 1. So this would be x ln x minus integral 1 dx, or just integral dx. And the answer would be x ln x, integral dx is x, and you add c plus c. This would be the integral of ln x dx. If you find the derivative of this and use the product formula to find the derivative of x times ln x, you will get ln x. Another example, and here I will teach you a method to find this integral quickly, because if you use the usual setup, you have here, this is algebraic and this is exponential, and we know the word L-I-A-T-E, so A before E, so U should be T square, and dV should be ET dt. Then du would be 2t dt, and v would be et. The integral of dv is v, and the integral of et is et. Notice here that if you use the usual method, then this integral I would be equal to uv, which is t square times et, minus integral v du, which is 2t, I will write 2 outside, t times et dt. So this integral, the new integral, is easier than the previous one, because here we have 2 square and now we have t. But still, we need to use integration by parts another time to find this integral. If I call this integral double I and work here to find this integral, I will take u equals t because it's algebraic, and du would be dt, and dv would be et dt. Take the integral, so you will have this one, and then double I, which is this integral without the negative 2, equals uv, which is TET, minus v du, which is integral ET dt. And you notice now that the t has gone, and now we can integrate ET easily. The integral of ET is ET actually. So the final answer would be t square ET minus 2 times this. So it would be minus 2TET, and minus 2 times negative ET, so it would be plus 2ET, and we add C. So we used integration by parts twice. There is another method which I can use, which could be easier than this. We use this method if the function that we are finding its derivative, which is t square here in the original question, u is t square and dv is e to the power t dt. So u is t square and the function we are integrating is et. So you make this table, and then this is the function we derive. So find the derivative of t square, 2t, and find the derivative again, 2, and find the derivative again until you reach 0. So to use this method, that u has to be an algebraic function, and it has the derivative at the end should be 0. If the derivative cannot reach 0, then you cannot use this method. And the integral of et is et, integral again et, integral again of et is et. And then you change the signs. You write some signs here. The first number here, or the first term, you put plus, then minus, plus, minus, alternatively. And you multiply this times this, and this times this, and this times this. So this will give you immediately the answer. So integral of t square et dt by this method would be t squared times et, and then minus sign 2t times et, and then plus sign, and 2 times et plus c. And you can see that it is exactly the same answer. All right. So I will use this method whenever it's possible because it's easier than using integration by parts twice like this. For example, I could have used this method here with x sine x, okay, with x sine x. Although x has power 1, it's okay. You can use it with power 1, power 2, power 3, whatever the power of the algebraic expression is. So u is the function we find its derivative, which is x. What is the derivative of x1? What is the derivative of 1, 0? And dv, the function we integrate here, is sine x. Integral of sine is negative cosine. Integral of negative cosine is negative sine. Then we put signs here. Plus, always you start with plus, minus plus, and you multiply like this. So immediately integral x sine x dx would be equal to x times negative cosine, or I will write it negative x cosine x, and then negative 1 times negative sine would be plus sine, and plus c, and that's exactly the same answer. Here, of course, you cannot use this method because you don't have an algebraic function. Here again, you cannot use this method because you do not have an algebraic function. So if you take u ex, the derivative would be ex. It will never go to 0. So what to do here? Well, this is a special integral, special case. You will see something here that uh, you will never see it again, except with another example in the next section. Look what would happen. If you choose u, of course, what do we have here? We have exponential and trigonometric. So I should choose u equals sine and exponential to be dv. It's okay. It's no problem. Let me do it like this. Although here, if you choose u, the exponential sine x is dv will work also. Let me check. Let me use u sine x, and du would be here derivative of sine, which is cosine x dx, and dv would be ex dx, and the integral of dv is v, and the integral of ex dx would be ex. Let me call this integral I. So I would be equal to uv, which is ex sine x, minus integral ex cosine x dx. And now notice that the original integral is similar to this integral. This one is not easier or more difficult. In similar, uh, يعني difficult like each other. يعني. So what happened? We will take this integral, which is double I, let me call it double I, and evaluate this integral here, also by parts. So again, I have exponential and trigonometric, so I'll take the trigonometric as u. So u equals cosine. The derivative of cosine is negative sine x dx, and dv is ex dx, and the integral of dv is v, and the integral of ex is ex. So double I would be equal to this integral, ex cosine x minus integral v du, which is ex sine x, and there is a negative sign, so it would be positive. All right, so let me rewrite what we have again. I have integral ex sine x dx equals, which is I, equals ex sine x, this one, minus double I. So minus ex cosine x minus integral ex sine x dx. Okay, notice that this integral is the original one. So we went back to the original integral. So what should we do here in this situation? Well, I take this integral to the other side. So it would be positive, and this is also positive. So we add these two integrals, and we get 2 times integral of ex sine x dx equals ex, I'll take ex common factor, sine x minus cosine x. So now, if you divide by 2 both sides, you will get the integral of ex sine x. And we can add c. So that's the answer. So this is what happened. We reach another integral which is similar to this in difficulty, ex cosine x. And then when we used integration by parts another time, we get the original integral. So we take it to the other side and we find the integral like this. I told you this is a strange example. Keep it in mind. You will never find like it again except in another one example. Now what happens if we have AB, if we are dealing with definite integral? Well, here f of x, g of x is the answer. So you evaluate f of x, gx from a to b, and the new integral would be also from a to b. That's it. So for example here, what should we do? We take u tan inverse x. Du would be the derivative of tan inverse, which is 1 over 1 plus x squared dx. And dv would be taken as dx. And the integral would be v equals x. So notice that we can find L integral ln integral tan inverse like this using integration by parts. So integral from 0 to 1 tan inverse x dx would be equal to uv, which is x tan inverse x, and I can evaluate this from 0 to 1, minus integral from 0 to 1 of what? V du, which is x times 1 over 1 plus x squared, or x over 1 plus x squared dx. And we need to find this integral. So I'll call this integral double I, and I'll find it here. So how to solve, how to find this integral? If you notice, the derivative of 1 plus x squared is 2x. So we can solve it by substitution. So we can let u equals 1 plus x squared. Then du would be 2x dx. And then this integral, we will write it. Also, let us find the new limits. When x is 0, u would be 1 plus 0, which is 1. And if x is 1, u would be 1 plus 1 squared, which is 2. So I have integral from 0 to 1. I have x over 1 plus x squared dx. But I need 2x, so I'll multiply by 2 here and here. So this would be half integral. Now 0 will be replaced by 1. 1 will be replaced by 2. 2x dx is just du, and 1 plus x squared is u. And now we changed the variables from x to u. And the integral of du over u is ln u from 1 to 2. So I'll have half times ln 2 minus ln 1. But ln 1 is 0, so it is half ln 2. So the answer would be, if I replace x by 1 here, I'll have tan inverse 1 times 1 minus 0 times tan inverse 0. So the answer is 0, minus double I, which is half ln 2. Tan inverse 1 is pi over 4. And if you want, you can take half up as a power of 2, because this is a property of the logarithmic function. You can write it 2 to the power half, or just I can write it square root of 2. So this is the final answer. Enjoy integration by parts and study hard.